historical insights from viewing quaternionic interpolation of three-dimensional rotations as a geodesic vector interpolation on $S to the 2 power. Oh, that's it's written in the LaTeX language. So not to forget about the $sign part. S squared. Okay, Bob, we're ready for you.
All right. I'm ready for you.
What a mouthful that was to just introduce your talk.
Oh my God.
Yes, computational advantages and historical insights from viewing quaternionic interpolation of three-dimensional rotations as a geometric vector interpolation on S squared. Say that 3 times fast. Okay, so plug that in.
Let me get this one up.
Yeah, let's get mine out. Yeah, let's take mine out. Okay.
Thing, or should I just stand here? I can stand here at a point.
So that would be for 20 minutes, so that would be 4:05. I'll just do it by sight.
I'll watch it for this too. Good.
Okay.
Okay. So and there's the abstract. Interpolation of rotations is the problem, and quaternionic methods is one of the solutions. But I'll talk about. I'll get back to Euler and Rodriguez. There may be a few repeat slides from last year for those who weren't there. A few that would be amusing, and there is a sort of a perception I've gotten from some people, probably not universal, I won't project it on everyone, that to interpolate rotations, the only way to do it is using quaternions. So I'll start with a way you can interpolate rotations just directly with rotation matrices. That's kind of fun. And so the interpolation problem to start with is you have 2 rotation matrices, as David mentioned also, that these are matrices that are, their transpose is their inverse. Euler in the mid-1700s does this beautiful paper that says that if we know R transpose R equals the identity, then automatically R transpose is the identity. Does it in a couple of stages from the 3x3 and the 4x4 just by hand. That's a really fun paper. And determinant R is +1, not -1. It's either going to be plus or -1, but the rotations are the +1 component, the connected component of the identity. Things are different if you include reflections. Interpolate from 0 to 1 some function, a path from one to the other in the special orthogonal group, in the rotation group, with one of them rotations at 0 and one at 1. And linear interpolation doesn't work because it won't be in general won't remain an orthogonal matrix. So you can't just interpolate the matrices component by component. So what are you gonna do? Well, what's the right analog? In fact, it's sort of an ill-defined problem. There are lots of paths from one to the other. What's so special about a particular one? This is a little bit like the gamma function problem. There are lots of functions that interpolate factorial, right? You can take any function between 0 and 1 and then use the factorial functional recurrence and get an interpolation of factorial. There's only one whose logarithm is convex. That's one of my favorite old classical theorems, the Bohr and Mallerup, that what makes the gamma function unique is it's the only one whose logarithm is convex. Otherwise, there are lots. So there are lots of interpolations. What's good about this? It's the one that generalizes a line. What's the generalization of a line? A geodesic. Shortest path if you have a metric, like a Riemannian metric. Well, fortunately, the orthogonal group is a Lie group. It's a Riemannian manifold translation invariant metric, so you shift every point along a geodesic, you will still get a geodesic. So it's like, wait, I can interpolate, and foreshadowing, the same is true for S3, the twice exponential domain, fundamental domain. So quickly, there's a pretty straightforward theoretical way of interpolating two rotations. Just, oh, whoops, this is just the Lie group stuff for those who might like it. It's the exponential map, the differential equation in the rotation group, that the computation that says that the derivative at the identity of an orthogonal matrix is an antisymmetric matrix. There's that one computation that's really nice. And the rotation by axis around unit axis u by angle theta is the exponential. You can really do this term by term by the infinite series for matrices. You get the identity plus this squared plus this cubed. And when you get that, you get actually the Euler-Rodriguez formula. That's literally, we talked about that last time. So, and interesting thing, the axis of a rotation, a lot of people use an eigenvalue and try and find a one eigenvector because it's a cubic, but you can actually just take the antisymmetric part of a rotation matrix and the axis is manifest there with just additions, no multiplications. The antisymmetric part of a rotation matrix, it contains in this form the axis. But if that happens to be 0, in other words a half-turn rotation, then you just have to add the identity, and that's another way. So you never need to do a single multiplication to find the axis of a rotation. Just add the matrix to its transpose. Or, and if you get 0, add the identity to the matrix. Kind of fun fact. So here's direct matrix interpolation. Translate everything back to the identity by multiplying by R0 inverse. You now interpolate I to R0 inverse R1. Well, from the identity to anything is just rotate around its axis. And that is a geodesic. So just do the exponential map on this, which you can find its axis by that method of finding the antisymmetric part, or 1 plus if it happens to be a half-turn rotation, and then multiply back by R0. So that's how you actually would do it, but that's a lot of work, and quaternions are nicer. So here's sort of a, here's reviewing from last time how I, and I think Rodriguez, think of quaternions, thought of quaternions, is arc addition on S2. A unit quaternion is just literally geometry is measuring the Earth. If you do vector addition on the Earth, you have quaternion multiplication. Literally, if I know this arc, it's the equivalent, just like vector addition along its great circle, that's the same unit quaternion. And this is the same unit quaternion. Any two great circles always intersect. I can find their intersection point, put the head of one at the tail of the other, just like in your picture earlier. Find the geodesic arc from the start of the first to the end of the second. That's quaternion multiplication. That's isomorphic to quaternion multiplication. So essentially it's the fact that the scalar part of quaternion multiplication is scalar 1, scalar 2 minus vector 1 dot vector 2. The vector part is scalar 1 vector 2 plus scalar 2 vector 1 plus the cross product. And that's just a really neat little identity of 3 unit vectors, 3 points on S2. For any 3 unit vectors, A, B, and C, if I know A dot B, B dot C, that's the scalar 1, scalar 2, vector 1, vector 2. then I get the dot product of the first with the third. And similarly for the cross product, A cross C, scalar 1, vector 2, scalar 2, vector 1, plus vector 1 cross vector 2. Neat little vector identity, which is essentially manifest in Rodriguez's paper about 4 years before Hamilton. And so here was a video of equivalence classes of ordered pairs of unit vectors in R3, and a calculator where you can actually look at lots of different equivalent representatives of a quaternion as a first unit vector and a second. So I'm just going to go on. And then here is quaternion multiplication as that triple of unit vectors or vector addition on the sphere. It is. And you can choose different, on my little calculator, you can choose lots of different options. Regarding the map from unit quaternions to rotations by conjugation that you did put up, it's absolutely true and a great way for geometers to understand that, but that's computationally never what you want to do because it's so many multiplications to perform a rotation by conjugating a pure vector quaternion by a general unit quaternion. That's 4 times 3 and then by another 4. That's a lot of multiplications. So the preferred way, there are two ways. If you think of things as two unit vectors, you get the rotation, the same thing as the conjugation, by reflecting across the first and reflecting across the second with just a couple dot products. Amazing. There's the formula. Reflection across is 2v dot u minus v. You do that twice, and if you're doing just a few vectors like for computer graphics, it's way fast. The other way, the more generic and standard way, here's a little, where's my, whoops, I can go back and play the video. This is just to show how the product of two rotations is a reflection, reflections is a rotation by twice the angle. I did a reflect across noon and 2, I get the rotation from 12 to 4. There it is in 3D. The other way, the standard way, is Euler-Schumacher. And here is literally Euler's formula for, here's the force, the 3 sphere in R4 if you make this equal to 1 and you don't normalize. So if you have a unit quaternion, Euler wrote down the map from S3 unit quaternions to SO3. This gets you a orthogonal matrix. Really nice. And that's what Schumacher liked to do. So it's a 9 multiplication transform. Anytime you need to go back and actually implement the rotations, there's no better way than multiplying by a matrix. But when you want to compose, much better to multiply the quaternions. And much better to keep orientation in robotics. Spurrier did some work in the robotics field too, and he did the reverse matrix to quaternion, which isn't a one-to-one, right? Since it's 2 one-ways, it's not onto. So there's the rocketry and robotics. So Hamilton wrote, as from last year, on Rodriguez and Hamilton. Rodriguez understood this about rotations. Here's some of the pictures, and there's where spherical triangles came in. And Rodriguez, we have here the translation in the original. I think I may have brought this slide from last time that showed exactly. Rodriguez says there's a perfect analogy from composition of rotations between composition of translations and an ordinary rectilinear triangle, and composition of 3D rotations and spherical triangles. Amazing. I was like, smart guy. And there's the derivation, which is in the trigonometric form, which he has written down. Those formulas, which were scalar 1, scalar 2, minus vector 1, vector 2, scalar 1, vector 2, scalar 1, vector 2, plus scalar 2. You see it all there. And here's the original 2. There's, and you can see in there the cross product and the dot product using, so, and Euler even had wrote down the cross product as the infinitesimal axis of a rotation in 1752. So they were playing around with, at least in coordinates, with dot products and cross products and knew their geometric interpretation in the 1700s very well. Yeah, there it is. There's beautiful, the scalar part and vector part in 1840, 1841 in the most well-known journal in Europe. And here's the correspondence between rectilinear triangles and spherical triangles, literally translated, and you can see it in the French, in Liouville's journal. There it is, along with Lamé and Delaunay and Cauchy, and yeah, everybody knew this, and even Cayley himself wrote about this article in 1843, again before Hamilton's bridge. And I was saying, and Lebesgue, and I think, who was it? It was Eli Stein said, wrong Lebesgue, Bob. He was much later than this. It's like, not the Lebesgue integration? No, sorry, apparently not. I guess I was wrong about that. So there's some other Lebesgue in the 1800s. Anyway, and there's Cayley on there in 1843, before Quaternion. So this was, they were very aware of this. So now here, the difference, now here's Quaternion multiplication is first, second, second, third, first, third, in terms of unit vectors. If you combine, if you find the common first vector instead of first with last, first with second, like vector addition, well, think of it in Rn. How do you interpolate two translations? You put their starting points at the beginning, but in common, and then you interpolate the endpoints. Do the same thing. I mean, it's sort of natural. So if I take any two quaternion classes and find the intersection, the overlap, where they have the same first unit vector, then I can just interpolate the second, and that will actually be quaternion interpolation right on S2, which is much more efficient actually than what's usually done by Schumacher, is doing interpolation on S3. I'm reducing the dimension by one. And so that's sort of what I will point out. And you can do vector addition there. That's how you can do your vector addition. So here, oh, this is just not a unit, not a problem. It doesn't matter. This applies not only to unit quaternions, but here is spherical. So it's just the linearity in the second component, but the formula still involves, spherical linear interpolation involves the dot product of the full four-component quaternion. And the nice little bit of algebra with the, what's it called, Cauchy-Binet-Cauchy identity says that this dot product will be just the dot product of the second vectors when you've made the first unit vectors the same. That's the essence of the calculation, is that this becomes just this dot this. Okay? So you reduce it from four-dimensional vectors to three-dimensional vectors. Great, 5 minutes. And so here is the picture of interpolation of unit quaternions viewed as ordered pairs of unit vectors, when I can take any two, I can find a pair of representatives sharing the common first unit vector. Here's the first, here's the first second vector, here's the second vector. I've set up a flash thing, and now I interpolate, and what it means is you're doing that. So you can think of this as arcs on the unit sphere, and I'm using this algorithm to do the rotation. Reflect across mouse, reflect across mouse 1, reflect across midpoint of mouse 1 and mouse 2. And do it in reverse to the camera. And that's how I pull my thing with the mouse. Anyway, I can send you links to these, but this literally demonstrates quaternion interpolation. Observation of our Palais, not me, one with the S in the middle, says, you know, you don't have to computationally do this with transcendental functions. You take this vector and this vector, how can I interpolate them on a unit sphere, either in 4 or 3 dimensions, whichever you prefer? Find the bisector. Just add them up and divide by the square root of the sum of the squares. Do it again, bisector. And every time you do further bisection, it only requires one new normalization factor, because all the midpoints have the same length. All the midpoints have the same length, or all the sums have the same length, so you do one, once and for all, 1 over square root, and multiply all the components. So you only need square roots, or a -1/2 power, to find a nice interpolating curve on a sphere. And wait a minute, you only have to do that to find the FFT twiddle factors. You don't need sines and cosines to find the fast Fourier transform twiddle factors, or you don't need a complex exponential. Just do addition, normalize, right? You get the points of the regular 2 to the n gone. Those are the twiddle factors. That's how how the ancient Greeks did it. I probably have a minute. Back to spherical triangles, last 2 slides. Good, back, last 2 slides. The area, this is from about, I think the 1600s, no, even the 1400s. Gerard and Harriet both found nice, just classical geometry, that the area of a spherical triangle is the sum of the angles minus pi on the unit sphere. Now think about that, because Archimedes knew that the area of a sphere is the area of the circumcylinder, around and up. So that's the equal of the circumference times the diameter. Okay, well, that means I know that 2 times 2 pi. Okay, it's 4 pi. How many of these triangles, how can these triangles fit exactly, some number of triangles fit on a sphere? There are only 3 possible ways. Of course, you know that, the tetrahedron, the octahedron, and the icosahedron, the one that's not the pentagons. There are 3 Platonic regular sphere decompositions, and it's a very easy way to show it. Combine Archimedes' 4 pi and Harriet Gerard's some of the areas. That's a nice classification of triangular Platonic solids. Now, last thing is this. Eratosthenes, we all know that Eratosthenes figured out the circumference of the Earth. But he went 60 miles north, so it was 1 degree, 60 times 360 is about 25,000, or exactly 25,000 for our purposes. And so Eratosthenes knew it was 25,000. Archimedes, back to his, okay, cool. Archimedes knew that the diameter is the circumference over 3 1/8. He knew pi was he figured out very early that pi was exactly 3 1/8. And what's 3 1/8? That's 25/8. So if you divide 25 by 25/8, Archimedes knew that the diameter of the Earth was 8,000 miles. And since Archimedes was working in miles, he could go in his head and say 25,000 times 8,000 and say the area of the Earth is 200 million square miles. Isn't it nice that Archimedes was using miles? I guess. Go to Google Earth, 197, within 2%. I think it was sort of amazing, because I've never heard, I said, wait, is this anachronistic? If Eratosthenes was after Archimedes, that would be a problem. But they were contemporaries, they were friends, they wrote to each other, they dedicated work to each other. And I've never heard it mentioned that Archimedes' calculation of the area of a sphere could have allowed him, it must have. Eratosthenes, hey, I figured out the circumference of the sphere. Well, I figured out the area of the, of the Earth. That must have been what he was doing, but I Googled area of the Earth, Archimedes. No one points that out. It's like he had to. I think he had to have done that. I mean, they were friends and they were calculating these things. He talked about it in the sand reckoner. But so, and fortunately for him, he was doing it in miles, so he didn't need to use a calculator.
Miles?
You heard it first here. Stadia, actually.
English system?
Yes.
Before the English.
Fake news. Okay.
Okay, thank you so much, Bob. And Bob, that was very exciting, very interesting.
Always fun.
Yeah, it was fun. Okay, any questions for Bob about his wonderful presentation? Okay, our next speaker, I believe, is going to be Pengelley. I'm having some trouble with the app here for coffee or something. So next, yeah, having some problems with that.
My panel is at 4:30, so go out, get things ready, and come back until the panel starts. But I want to make sure they have my slides. Well, only well. Yeah, but it's not, my panel is at 4:30, so I'll get to see the first few minutes.
You're the next speaker.
It's in 3:15.
Okay, so
It's very nearby.
and do you have the
I'm
name
going
to
to
introduce it? I mean, I think for some reason my app isn't going so well. Yeah, I mean, I don't know why, but it's not. Yeah, see, look, it says mine, it says Heshne's, and then it says next, and the other ones. And I did get Quaternions too. It's like it's just not. Okay, so you'll thank you, yeah, because I don't have the name of the room. Did you want your own?
I have mine.
Oh, great. Okay, do you need are you a Mac or
PC.
PC? Okay, PC, wait. Oh, you have the H thing, is that? Go over there and grab some stuff like that. Oh, yeah, I had a major curvature issue and gravity set in. Yes.
Should we meet down in the library, in the lobby?
The library.
The lobby of downtown?
You mean on the first floor where the computers are?
The lobby.
You know, oh, you said, I thought you said the library.
The
Lobby. Oh, okay, yeah, we can pick down the lobby.
At what time? What time do you want to go?
Let me ask Bob, because he's also coming. Let's see what the problem, yeah, is he gonna be back? Okay, when he comes back, he's gonna help we'll set it up.
Okay.
Unless you wanna go, I mean, I don't know. If you
I'm
want-
going to his,
Right, so why don't you and Bob discuss it and then tell me where you're gonna meet? How about that? And then you
I
can
would like
easily
somebody to be my
organize.
helper. You can either be my helper and therefore not do your typing stuff,
Okay.
or someone else can be my
Okay,
helper.
I'll be the helper.
You're going to be my helper.
Okay.
Thank you. Okay, you just stand there and wait. You're going to be my helper. Okay. And this is to be done in pairs. So everyone I hand one of these to should find a friend, like maybe that man over there. You introduce yourself to a friend. Maybe the person behind you, and you are now a pair. Everybody's a pair here. Naveen, you may introduce yourself to him. You're a pair. This is called active learning. You may introduce yourself to him. And you can find a friend too when somebody else walks in the door. Okay? And I will be right back. I have 2 minutes.
what?
I feel like an arranged meetings in a cat. There's this. We all meet in the Simpson lobby. Actually, on Friday. But I can't make it this time. Oh, but maybe this time. Yes.
Somebody should maybe get a reservation.
We just walked in. When you went there.
It was fine.
It was fine, yeah. It was fairly good. Yesterday.
What time is it?
That was actually about 8. We went about 8 to 8:09.
It's kind of late.
Which is kind of late because we tend to be late people, but that's okay. We can go right away. Just see what this is doing. Maybe. Let me take some.
So who came in and doesn't have one of these? So this is teamwork. You need to find a friend in the room. So I want you to find a friend and introduce yourself. We're going to share this. Maybe that's your friend there. Okay. Anyone else who needs a friend? Okay. Well, you're going to be his friend. Okay. You're going to work together. Okay. Introduce yourselves. Okay. I'm ready when you are, Johannes.
Okay, sure. All right. Okay, so this is Bob Pengelley, and he's going to be talking on. I don't have those. Oh, okay.
Right there.
Oh, how can symmetries of a rectangle, third up to homotopy, provide a physical model for the Quaternion group? Generalizations.
Is that as long or shorter than Bob's title?
I think Bob's title was actually.
Okay. So this is joint work with Bill Bogley. I'm David Pengelley. Welcome. As we all should know by now, we all, including our students, learn much more if we're a little bit involved instead of just listening to a lecture. So I'm applying that to ourselves as well as our students. So that's why you have a friend and something to work on today. And we're going to begin with that. So you have a rectangle and a strip. What are the rules and which group is it? So the rule is that your partner holds the end of the strip. So, here we are. You, the person who has the gadget, will hold it like this, and your partner, that's my partner, Johannes, he will hold the end of the strip like this. Now, Johannes has a very boring role here. He is to stand here and do nothing. In particular, he should not move his hand, and he should not move the strip. Okay? Now, you, on the other hand, with your partner there, you, on the other hand, are allowed to move the rectangle. And you're allowed to move it to perform symmetries of the rectangle. Now, hold that for just a moment. So if we just have, hold my rectangle, thank you. If you just have the rectangle without the strip, what kind of rotational symmetries do we have for the rectangle? There are 4 of them. There's the identity, there's the half-turn, which I'll call rotation, there's this one which I'll call spin, and there's this one which I'll call flip. And together those form what group? The Klein-4 group. Thank you very much. So we have the Klein-4 group as the rotational symmetries of the rectangle. Now we're going to make life a little more interesting and complicated because we're still going to perform rotational symmetries of the rectangle, but now the strip goes along for the ride. So for example, it's possible that this version of the rotation of the rectangle and this version, which are producing the same rotation of the rectangle, might not be, the strip may look very different depending on which way I turn my rectangle. And we are allowed to play with the strips. So this is up to isotopy of strips. So he doesn't move his end, and I don't move this end. But for example, this situation is equivalent to this situation, which is equivalent to this situation, which is equivalent to this situation. You get the idea? You're allowed to play with the strip after turning the rectangle, but you don't return the rectangle. The rectangle turns, it does something, it performs a motion, and then you're allowed to play with the strip. So let's see what there are in the way of rules. The far end of the strip has to remain fixed. That's Johannes. We're considering rotational motions that end in a symmetry of the rectangle, like this, okay, up to isotopy of the strip, which is that you can play with the strip but not the ends. These compose to form a group, I promise you, and the question is, which group is it? And you get one hint, and unfortunately only 3 minutes to work on this. The hint is the Philippine candle dance. Johannes, you can hold this. The hint is the Philippine candle dance. Here you go, Deepak. The hint is the Philippine candle dance. Now, here's part of the Philippine candle dance, which is a little bit like the double trick in case you've heard of it. So watch this, okay? Watch my hand. There's a candle in my hand. It will not tip. My hand remains facing up the whole time. I'm going to perform, you can do this too, 1 full rotation of your hand like this. That's 1 full rotation around the vertical axis. And now I'm going to continue and perform a 2nd full rotation in the same direction around the vertical axis. And you will imagine that my arm is going to break, but it doesn't. Because amazingly, when I perform the 2nd full turn of my hand around the vertical axis, this twist in my arm goes away. Now that's your hint for figuring out what group this is. Okay, you have 3 minutes to see what you can figure out about this group. I wish you had a little longer, but you don't. Deepak, work with the woman behind you. She's your partner. Okay?
David, are you? David. Gary.
All right, everybody needs to get going here. Get going with your partner. This way. Fast participation. Who needs another rectangle and strip?
Yeah, Gary, are you 2 working together now?
Well, I don't know.
Thank you.
No, I'm confused. Okay.
That was okay.
Now, be good students. You've only got 3 minutes. Who needs help?
And then I guess what we're doing is kind of like a belt trick. Yeah, oh yeah. That has an extra.
That means if I do
where, Bob, what is you? Okay, so I kind of lost track. I think we're trying to do something similar to the double belt torch. Exactly. Not helping big. Yeah, everybody. Yeah, we're trying to do. No, you're not. No, he's supposed to be doing it. This is the group. This is the group. Okay, representation. Switch part, switch sides.
I mean, I don't know if it's
Yes, right, I know. Okay.
So is that good?
Oh, yes, right, you did it last year.
Something else. Otherwise, it's almost like.
Okay.
It's still attached. Well, it's not attached to the center anymore. Yeah, because I do see that as a different thing.
Right.
That's with the twist now.
Yeah.
So this would be like generating sequence. Right? I think that part of it would be Z spinning it around this way.
That's called the famous.
No twist.
It's also in, yeah, this is in Wheeler, and it's,
But then there's the other thing. Then there's rotating.
Now, I'm very sorry to stop you, but Johannes is only giving me 20 minutes for this whole thing, and you are doing wonderful work as students in active learning, I would love to just let you keep going for another 20 minutes, half hour, whatever, okay, but those aren't the rules of the game here. So you've done wonderful work. Good things are happening. I would like to get these back from you after the talk, please. I need them for tomorrow when I'll be giving a presentation in a session about active learning in the classroom with hands-on manipulatives, and it will be using exactly these. So if you'd like to come to that and do some more with some other people, that'd be great. But I'm going to continue on now. Now, what have you, very quickly, in 30 seconds or less, what cool things have you figured out here?
a group of order 4.
A group of
order 4.
Sixth group of order 4, someone says. So you've discovered an element of order 4 in particular, is that right? So what's the element of order 4 here? With the rectangle, what do you do to create the element of order 4? Half turn. Half turn is an element of order 4. Now in the rectangle group it was of order 2 because 2 half turns is the identity. But with the strip it's not. Okay? But 2 full turns is the identity because of this trick, right? So that's 4 half turns. So you've discovered that this element of order 2 in the symmetry group of the rectangle has become of order 4 when we attach the strip. Good. Okay, so there's an element of order 4. Are there multiple elements of order 4, do you think, here? Didn't we see 3 different rotations of the rectangle around different axes? I wonder if those would produce different symmetries of the rectangle, right? So they have to be different in this group too. It's just that their orders are going to increase. So I think we've got maybe multiple elements of order 4. Does anyone want to make a wild guess? You've got 10 seconds to make a wild guess about this group.
Z4 cross Z4 cross.
Z4, okay. Good guesses. Okay, so what is this group? What's the title of this session?
Quaternion.
Quaternions, okay. Do you know a nice small group that has to do with the quaternions?
Quaternion group?
How about the 8-element quaternion group? Okay, so this is the 8-element quaternion group. It has 6 elements of order 4, 1 element of order 2, and the identity. That's the quaternion group. That's what this group is. I'm sorry to spill the beans, okay, but you can come tomorrow and explain more if you like. So what are we playing with here? Let's consider not just a rectangle, but let's consider any object in three-dimensional space. We're talking about first the rotational symmetry group of the object, which in the case of the rectangle was the Klein 4 group, and then we're talking about this strip group, which I've created by attaching a strip to it. So it's equivalence classes of strips resulting from rotational motions of X with an attached strip that end in a symmetry of X up to isotopy of the strips. That's this group, okay? And there's group structure, and now there's another group that I'd like to introduce to you, which I'll call the motion group. Now, unfortunately, mathematicians tend to call symmetries motions, but they have nothing to do with motion. A symmetry is a symmetry. It's just doesn't have to do with motion, but this has to do with motion. Okay, these are real motions. So what we've got here is the rotational motions of X, or the rectangle, that end in a symmetry of X up to, in fact, homotopy of motions preserving the ends. And so it won't come as a surprise to you that this strip group is actually this motion group I've just defined here, where we don't mention the word strip, but it's a rotational motion group of X. So now I'd like to go on and share with you, first of all, a little bit of general homotopy theoretic stuff that I won't go into details of, but what's going on here is that the rotational symmetries of any object are sitting inside SO3 here, the isometries of 3 space, and over that we have the unit quaternions. Over this, I'll call this the unit quaternions, and in fact you can look at what's called the path space of paths beginning at the identity in SO3 and ending at some other point in SO3, and this in fact is the unit quaternions. The motion group sits inside that. So what we have here is the motion group sitting inside essentially the quaternions. And as was mentioned in the previous talk, the unit quaternions is a twofold cover of SO3. The kernel is of this group homomorphism, and it is a group homomorphism. Hamilton's very clear about that in his lectures on quaternions. He describes exactly this group homomorphism for us. It's conjugation by a unit quaternion. The kernel is plus or minus 1. Guess what the minus 1 is? The minus 1 is the full turn. The minus 1 is the one full turn that's going to be of order 2. After all, minus 1 should be of order 2 in terms of multiplication. And so what we have here is that for every object X, we have a motion group, and it's a twofold group theoretic cover of the rotational symmetries of X. And all I'd like to do with you now in the few minutes remaining is I'd like to share with you just a little bit in the way of other examples of this other than the rectangle, but related to the rectangle. So this thing seems to have stopped working. So I'm just going to try this. Fortunately, this still goes. Okay. So first of all, there's an interesting little lemma here, group theoretic, about how this covering works. So if you take an element of SO3 of order n, for example, an nth of a turn, okay, then the inverse image up in the unit quaternions consists of 2 unit quaternions, q and minus q. And what about their orders? So the order of the inverse images of a rotation in SO3 up here are either both of order 2n, don't worry about it, Johannes, thank you, of order 2n if n is even, or one is of order n and the other is of order 2n if n is odd. This is not too hard to figure out, but this is what happens. And one corollary of this is that the motion group has exactly one element of order 2, and in fact it's that full rotation that we just talked about. It always has just one element of order 2. And another corollary of this is that this projection of the motion group to the rotational symmetry groups, this twofold cover by Z2, is not split if the rotational symmetry group has even order, but in fact it is split if the rotational symmetry group has odd order. So we can begin to look at this group theoretic covering and what's going on here. These, of course, are all subgroups of the unit quaternions. And now I just want to show you a few pictures and then end. So when you see the rectangle and you see these 3 colored axes, you might think that there's sort of a rectangle there. And when I talk about symmetries of the rectangle, those rotations around one axis, they will reverse the ends of a colored axis, but keep the axes. So for example, I rotate around the red axis, it will simply reverse the ends of the green and blue ones with each other. And so what we're looking at with the symmetries of the rectangle is really the symmetries of this colored axis picture. And when you see axes like that, you begin to think of a cube. And when you see a cube, you might even begin to think of a beautiful tetrahedron that sits inside this cube. Speaking of platonic solids, again from the last talk. And in fact, there are two beautiful tetrahedra sitting inside a cube, using either those 4 vertices or the other 4. And then you can ask about the symmetry groups of these and the motion groups associated with each of them and how they're all related to each other. And of course, we know that when you go from the rotational symmetries of the triple axis to the cube, you're going to have quarter rotations around the faces that you didn't have here. And you also, when you go to the cube or the tetrahedron, you're going to have third turns around the corners, and so you're going to get more complicated groups. And we could just look at those for a moment, and then we could end with the dodecahedron. So, so here, for example, is what happened. Now, we already know from your wonderful work that for the rectangle, the motion group over the Klein 4 group is going to be the 8-element unit quaternion group. Okay? We also know this doesn't split, remember, because this has even order. And now we can look at the tetrahedron. In the case of the tetrahedron, remember, we include then third turns around certain corners, and so it's not surprising that we might get something a bit bigger involving Z3, and in fact we get the semi-direct product of the Klein 4 group with Z3, and over that, in fact, we get what might be a lucky guess, we actually get the 8-element unit quaternion group, semi-direct product with Z3. So in other words, this semi-direct product splitting here passes up to the motion group, which is kind of interesting. And then you could wonder, well, what happens when I go to the cube? Now with the cube, something interesting happens. We have these quarter turns around faces of the cube that we didn't have for the tetrahedron. So this expands to S3, in fact, which begins to involve elements of even order, which is what somehow creates these elements of order 4 here. And then the group above this is actually well known to combinatorial group theorists. In fact, it's called the binary octahedral group. And you notice I haven't shown it as a semi-direct product. In fact, this semi-direct product doesn't lift. And here's a little lemma that one can also prove, and that is that if your rotational symmetry group is a semi-direct product, like this, then you can ask, well, gee, would this semi-direct product structure lift to here, like happened here? And indeed, you do get a short exact sequence of groups here using this H, which was the Z3 here at the bottom, and then P inverse of the K here. And if that splits, you could prove that the H at the bottom had to have odd order. And it did here have odd order, which allowed this to split. But here you notice S3 doesn't have odd order, and so this little lemma tells us that this splitting can't lift to the binary octahedral group as a splitting over there. And so maybe the last thing I want to show, my last slide, will be based on this really beautiful phenomenon that I didn't know until recently about the dodecahedron, and that is that a platonic cube sits inside the dodecahedron just like that, and in fact it sits inside in 5 different locations in the dodecahedron. How many people knew that you can embed a cube 5 beautiful different ways in a dodecahedron? Isn't that cool? I never knew that. And this plays out in the group theory associated with the rotational symmetry groups of the cubes, 5 of them, and the dodecahedron, and then in the motion groups as well. And it plays out like this. So this is like the previous slide, but I've added one more column here, the dodecahedron. But you notice I have to jump over here, and that's because although the cube embeds in the dodecahedron, its rotational symmetries aren't all rotational symmetries of the dodecahedron, because the quarter turn around a face of the cube is not a symmetry of the dodecahedron. So these symmetries do not all, that doesn't create a subgroup here, but I do have a bunch of ways of putting in tetrahedra, because I have 2 tetrahedra going into each cube, although they are producing the same symmetry subgroups, and those cubes go in 5 different ways in the dodecahedron. So there are actually 5 different ways that this will sit in here, which doesn't seem so surprising when you see A4 and A5. You could probably think, oh, 5, right? And so you wonder then, what's the motion group here? And it's known to combinatorial group theorists. It's the binary icosahedral group. And you could, again, wonder, well, of course, this is a simple group, the smallest non-abelian simple group, so we have no semi-direct product structure here to even imagine might lift to there. And you can begin to study this. You can look at the 2 CELO subgroups of these, which is fun and interesting to do, and I always forget the details here, but I will just tell you, for example, that, so this Q8 sits inside here in 5 different ways, corresponding to the 5 ways you can put a cube in. And so you have 5 different Q8s in here. The Q8s are the 2 CELO subgroups in here, but there are 5 of them, so it's not normal, which should come as no surprise. And let's see if there's anything else I wanted to say. Oh, just that for the cube, let's see if I can get this right. For the cube, the 2 CELO subgroup here is larger than the V because there are elements of order 2 here. So in fact, the 2 CELO subgroup in here is D4, from the square. And so in here, the 2 CELO subgroups, everything is twofold cover. So the 2 CELO subgroups in here, is Q16, called the generalized quaternion group. And it's there in 3 ways, because it's not normal, because there are 3 ways I can do this corresponding to 3 different axes where I could choose to put the quarter rotation. And corresponding to those 3 different choices of axis to put the quarter rotation, I get 3 2 CELO subgroups Q16 here, so it's not normal either. So this is a lot of fun. Bill and I are still working on this. This is a rather preliminary report, but I thought it would be fun stuff to share. Let me use my 1 minute. Johannes is the most terrifying person I know because he always stands up here and he's just a taskmaster. You have 1 minute left, you know. And I go, my God, he just put the fear of what into me, and I can't believe I ended a minute early. Oh, Johannes. Oh, it's so nice not to have Johannes' wrath. That's really great.
Okay, any questions? This was great. Thank you so much for being here. I know you were sort of not sure you would make it this year, but
happy to have this to share.
Yeah, but Chris and I convinced him to come this year because we had so much fun last year. So give a great hand to David Pengelley. Sorry, I'm nervous.
Okay.
Okay. Any questions, please?
What's the history of this idea of adding the strip and holding on to it? Is that something you came up with?
Well, that's a good question. No, I did not come up with it. So all I know about its history is that I learned it 20 years ago from Arkady Weintraub, who's a professor at the University of Oregon, when he was at New Mexico State University, where I was too. And I talked to him recently about this, and he said he learned this when he was a child in Russia. And so this comes, the track goes back at least 40, 50 years in Russia. I don't know what else to say than that. I will say the following. When I learned this from Arkady, I told him I thought I learned it as instead of a strip, you have 3 parallel strings. And that seems to make it a lot more complicated because you can move the strings independently. So you could do a double turn, and then instead of just moving the strip around, you could move the strings one at a time. And then you create these incredible knotted things. And you say, oh, I have no idea what's going on. And the question, of course, is whether the group is more complicated in the case of 3 parallel strings than with the strip. And it appears not to be. It appears that it's still the 8-element quaternion group, but I can't prove that yet.
Yet. Any other questions? Well, let's have a big hand.
Pengelley, thank you, Johannes. Okay. I'd love to have those back,
yes,
if you would.
Everybody,
leave them on the chairs or pass them forward. I need these tomorrow. Tomorrow what I'm going to do is talk about these strips and cards in an MAA session on tactile learning and how I've used this with everything from middle school students to upper level undergraduate students.
Anyone else have cards? You?
Oh,
Yes. Yeah, I got it.
Claiming that, then do what you can.
That's one full turn.
Right.
You need to do another full turn to get the identity. Now you're the identity because
Because you can do that.
yeah, tangle that strip.
Nothing has changed.
No,
nothing. We're staying on schedule.
Right.
Yeah, got it.
Yeah.
The second question, are you,
5:50.
since you weren't aware